Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today we will continue our lecture with on fatigue and fracture mechanics on lecture 7, fracture toughness testing. The outline of today's lecture is about the test specimen, testing procedures, and then calculation of K1C. Right. Could we determine the K1C, or we say that as fracture toughness? Fracture toughness K1C, the critical stress intensity in mode 1 fracture. Because 1 here is actually referring to the first mode 1, which is the crack opening mode, and then C is the critical stress intensity. Right. So you need to make sure that the specimen is tested under mode 1 fracture and in a plane strain condition, which it is in brittle condition. Okay, it's going to involve the following steps. The first one is the validation of K1C fracture toughness values, and then the specimen preparation. Next, the testing procedure, and the last one is the calculation of K1C value. Okay, the determination of K1C fracture toughness. The test method that should be used to obtain the critical K1C value for a specific material in a specific application depends on the type of expected or desired fracture behavior. If you want to assess the mechanical or the fracture mode of mode 1 or mode 2, so you need to apply the test method that's suitable for assessing the fracture mode. Okay, if you go to this specimen is about to happen the linear elastic mode or linear elastic problem, where the lowest value of fracture toughness occurs under linear elastic conditions, it resulting in sudden brittle fracture. If we go to into the second figure, this is the elastic plastic. Toughness of a given structural material increases either by decreasing temperatures, decreasing loading rate, or decreasing constraint. Elastic plastic behavior occurs. And then if you go into the last one, it is about the general yielding, the one that we have covered last time. Further increase in temperature or decrease in loading rate generally result in general yielding or fully plastic behavior. Okay, this is the types of specimen that we can use to assess what type of mode of fracture. Okay, ASTM E399 standard test method for plane strain fracture toughness of metallic materials. So this is one type of sample geometry. If you can see, this is mostly a flat curve, a flat surface, and then there is some kind of P here is as the force acting on the structure. A is the opening crack opening here, the length, and then we also have different type of length. This is mostly a circle, but they cut it here, and then you can see this the other specimen. But the one that we're going to check is, if you see here, I have a parameter A, W, B, P, and so on. The same like in this case, A, W, B, and P. So as long as you observe how much is the value of each parameter, you can just directly use this specimen into the required machine. So most likely, the rate inside the rate circle, two most common specimens used in various ASTM standards. Okay, this is the test specimen that we use. We always use this for, as I say, the 3-point bending test. So we call this as 3-point bend specimen. Okay, I have a, a stand here, or we call that as a support, as supports for the structure, and then I have a crack length here. W so 2 divided by W is the length from here to here. Also I have P. P is the force acting on the specimen. That's why you can see once I pull, I apply the force here, this structure due to the support here, it will bend. Okay, surely there will be some kind of assessment in terms of fatigue due to the crack length here. And then this is the B, the thickness of the specimen, where B is the weight, the height here. If you see from this view, W is the height divided by 2. While actually W is the thickness, but because we look from this view, so we say that this is the height of the specimen. Okay, this is the compact tension specimen, ASTM E399. A different type of specimen, but if you look this, I have 2 holes here, which is I can determine that value by using the 0.25 W. So you need to make sure the specimen is according to the standard. If I say W is several centimeter, so it means that every other thing like the hole, the width, which is deep, all of them depends on W, so we must follow the standard. Otherwise, the specimen is not valid. Okay, the validation of K1C value. The stress distribution under the notch varies due to specimen thickness, which also affect toughness of materials of different test specimen dimension. Okay, I have a test specimen, but at the edge of that, some kind of thin, medium, or thick. So we can plot here the thickness of B versus the fracture stress, and then we can check what type of mode that we're going to have. Like for example, in this region, I will get mixed mode fracture, while this region will be strain plane fracture. So this type of graph, if we obtain this type of graph, it is actually referring to the effect of specimen thickness on stress and mode of fracture. Alright, due to the criterion for brittle fracture in the presence of the notch, the plane strain condition is required for the validation of fracture toughness K1C values, where A, we understand that one as the crack depth, which is must be more than or equal to 2.5 times K1C divided by sigma yield strength, square root of them, not square root, the square of this term. B is the specimen thickness. So we must obey this rule. The specimen thickness must be more than this. Crack depth must be more than this. The specimen width must be more than this. Otherwise, you cannot use this term to assess the plane strain condition. Okay, for the specimen preparation, first you need to select the specimen dimensions. Of course, the specimen dimensions is actually you have to refer also to the capability or the limitation of the machine. So and then you need to select the crack propagation direction. So if you see in this figure, we have IL, and then LT, TS, ST, LS, SL. So all of them are actually coordinated by the transverse, longitudinal direction, or even the rolling direction or fogging axis. Okay, still under the specimen preparation, fatigue pre-cracking by applying fatigue load at a control condition of small load and amplitude to obtain a sharp fatigue pre-crack to ensure high stress distribution ahead of the crack tip. Okay, this is if you want to assess in terms of the fatigue loading. Let's say I put a specimen where this is the cross-sectional area. You can see I have the machine notch here, and then the fatigue crack is here. From here, they also apply the load where it will be an open crack opening mode. Only by doing this, you actually can see how much is the load as varies along with the increment of time. Okay, because we are talking about fatigue. Fatigue is actually depending to the time. Okay, this is the 3-point bend test setup. I believe that most of you have done this in the mechanical lab before. Even this one as well, compact specimen test setup. So this is the testing procedure. A pre-cracked specimen is arranged and monotonically loaded until failure. Before this, most likely we just use a specimen with some kind of notch. But for the fracture mechanics testing, we need to have a pre-cracked specimen. Means that you need to specify where is the location of the crack. If you see in this specimen, let's see into this specimen, I have a notch here, and then I also define where is the pre-crack location. Okay, load P and cleat gauge displacement delta are recorded during loading to give a graph, which will be used for the calculation. So this is some kind of example of P versus delta curve. You can see notch displacement is here, and then the load also will be plotted. So how could I know the type for each mode? Is actually depends on what is the trend of the graph. For example, I have this type of graph. I will have this as the type 1. And then if PQ, this is where if you see PS equal to PQ. Okay, this is type 2 where PQ is more than PS, but in this direction. So it kind of increase, but then suddenly drop to PS, and then it increase again. So if I get this type of graph, so this is going to be your type 2. This one, you can see PQ is above PS, but then it begin to decrease with respect to the notch displacement. So this one will be type 3. So once you obtain either it is about the compact specimen or in terms of bending specimen, doesn't matter as long as we have the data for the load notch displacement versus load. Okay, this is the calculation of K1C fracture toughness for compact specimen. It is actually most likely the same, almost the same technique that we have covered in the last chapter or the last lecture. Fracture toughness KQ is calculated using the following expression, where PQ is the load, B is the specimen thickness, W is the specimen weight. So F times A over W is actually the compliance function, where we have covered this in the last lecture, where we need to make sure the value that we select is actually according to AW ratio, A over W ratio, and then only by doing that you can get what is your value for FAW. So once you get where is the location of your design uh, based on the design thickness, design load, and then the design width, only that you can substitute the value by finding in terms of where is the value A over W, and then you can get F times A over W. But the same, like if you have a value between of two digit here, let's say 0. You let's say you want to assess on 0.453. So 0.453 is actually located in between 0.450 and 0.455. So you need to do the interpolation. Otherwise, you cannot get the exact value to be inserted here. Okay, for the bending specimen, fracture toughness KQ is calculated using the following expression. Okay, different equation. But this is for the bending specimen, this one for compact specimen. So the same point that you need to apply if you want to have KQ, you need to obtain what is the value of PQ, where PQ is the load applied on the specimen here. S is the span length. B is the specimen thickness here, and then W is the specimen width. F times A over W ratio is actually the compliance function that you can obtain from the same graph. This is not the same graph, this is a different graph, but using the same approach. Okay, calculation of K1C fracture toughness. This is the load gauge displacement graph, where X is the displacement while Y is about the loading. So from here you need to measure what is the value of PQ, what is Pmax. PQ is the applied load, Pmax is the allowable load. Then only that you know which type of fracture toughness here. Okay, if the load at every point on the P versus displacement, P displacement here, record which precedes PS is lower than PS, then PQ is PS. If there is a maximum load preceding PS that is larger than PS, then this load is PQ. If Pmax divided by PQ, this is the ratio, is greater than 1.10, the test is not valid test for calculating the fracture toughness, K1C. So this is the requirement for you to obtain the fracture toughness. So whenever you want to ask the question related to this question, you need to make sure that you select the correct type of assessment. So you need to measure what is Pmax, what is PQ. Only that you know, oh, at what position or at what mode that you are currently assessed. Okay, this is the data material This is what we call the thickness versus the fracture toughness, where this is a ductile region, this is a semi-brittle region, and then the last one is the brittle region. So from here, they make an approximation of the plot where it is about the tension, as in tension, and the other one is as in tension. So only by doing this, they know how to match into the graph. Okay, this is other issue of K1C test, where if I have a crack dimension, in this case, means that I need to assess in terms of the tip of the fatigue crack. So this is just the illustration from the band specimen. If I have this type of trend of the fatigue crack, so A1 is measured from the tip of the specimen to the tip of fatigue crack. So you take this point, what is the length, the same from here to here, and then the last one from here to here. So the reason is because they want to find what is the average crack length. So once you get that, you also need to determine what is the A surface, what is the crack length on the surface. So this one, there is some kind of issue that we need to obtain like A minus A on the surface must be divided by A must be lower than 0.1. Okay, this is one of the example so that you know what is actually being calculated here, because this is most likely on theory, but this is more on the example. Okay, a 3-point band specimen was tested and according to the STM E99 procedure. The 0.2% offset yield stress of the materials is sigma y equal to 1200 megapascal, and the modulus of elasticity is E equal to 210 gigapascal. The specimen was tested and at a loading rate of 100 kilonewton per minute, and a type 1 load displacement record was obtained. So remember, type 1 load displacement is according to this type of graph. A chevron starter notch was machined and the specimen was subjected to 30,000 cycles at Pmax equal to 45 kilonewton and Pmin, the load minimum load equal to 0. The final stage of fatigue crack growth was conducted for 50,000 cycles at P max or maximum load equal to 30 kilonewton and P min equal to 0. The specimen dimensions were measured as, so S is 30 centimeter, W equal to 8 centimeter, and then B equal to 4 centimeter. They also give you the value for A1, A2, and A3. And also A surface, the first one is 3.915 centimeter, and then the second one is 3.952 centimeter. Okay, there is a condition of the maximum load where the maximum load and the second load of the test record were measured as Pmax equal to 86 kilonewton and PQ equal to 80 kilonewton. So your task is to determine what is the fracture toughness, K1C. So this is the solution where first of all we need to determine a condition for K1C. KQ, we have A, so this is the what we call the I would say this is the average value. So you need to add A1, A2 and A3 and then divide by 3. And then you need to use the condition for both A surface, where if you see A minus A surface here divided by A must be less than 0.1 for both condition. Okay, once you apply this equation where you already obtained 4 centimeter, you need to apply it here and then you minus the first condition divided by 4. And then check the condition either it is less than 0.1. So the value you obtain here is 0.02, which is always less than 0.1. The same, you repeat the same procedure, and then you repeat the same procedure by using different value of a surface. Of course, you will get less value from 0.1 as well. So from here, you need to find what is the ratio between the maximum load and the PQ, the applied load, where the maximum is 86 kilonewton divided by 80 kilonewton. You obtain that as 1.075, which is less than 1.10. Okay, here it is actually based on this equation. P max divided by PQ must be less than 1.10. So like I mentioned just now, KQ that you need to calculate by using this equation, where you need to find what is the value for F times A over W using this table. So you need to find what is the ratio between A and W, and then you find where is the location that you need to take the value. Only that you can check and substitute that value into this equation. Okay, therefore, this is when they insert everything, so they get KQ equal to 70.5 MPa times square root of M. So you need to check either this condition is applicable for the test specimen. So check for A equal to crack length, which is 2.5 times this equation, this term. For the B specimen, either it obeys this condition or not. So based on the result, they mentioned that BA and then W is actually more than this term. So now it equal to 0.86 times 10 power of negative 2. So the above results indicate that all requirements of a valid K1C test according to the ASTM E399 standards are satisfied. Okay, and the conditional value KQ is equal to K1C, that is this value 70.5 megapascal times square root of M. So basically what you have solved here is actually to find either the specimen is applicable for the test or not, according to the rule and regulation that described in this requirement here in this slide. Okay, let's go to the value of critical stress intensity factor K1C and 0.2% of set. Yield stress delta Y at room temperatures for various alloys. So this is the sigma Y, while this is the unit in terms of MPa, megapascal, and this is KSI. So this is the fracture toughness SI unit, where this is the other unit. Okay, this is the range of each specimen or in terms of every material. So every material they have different yield stress and also different fracture toughness. Alright, next topic, we're going to talk about the fracture toughness testing as well, but it will be more deep into the application on uh, how that being applicable in the industry. Okay, without any, if you have the same, if you have any question or doubts, please ask during the lecture class online. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.